Okay guys, so hopefully we've been through this in the live lesson anyway because you were there, but just as a quick recap in case you need to check your notes or go through anything again, I'm going to run through the alkenes stuff just as our recap summary following on from the Education Perfect work. So alkanes was where we started. So you all seem pretty clear on the alkanes at this point, that we have methane, ethane, propane, butane, that their formula is CH4, C2H6, and the displayed formula. And you all seem to be reasonably good at splitting these down into the structural formulas. So remembering that it's each little carbon block. So this would be CH3, this would be CH2, and this would be CH3 to write it down. And we remember that the general formula is CnH2n plus 2. So you double the number of carbons and add 2 to get your alkane. And that's because each carbon needs 4 bonds. It needs to be completely filled up. So to do that, you need 2 extra hydrogens to go onto each end, essentially. So alkenes. So the alkenes are the next homologous series down. They have the ene ending instead of that alkane. There is no methane because you need this carbon-carbon double bond for something to be an alkene. And obviously, if you've only got 1 carbon, you can't put 2 bonds between a carbon because there's no other carbon to attach it to. And hydrogens only have 1 electron. They can only make a single bond. So methane does not exist. So our first alkene is ethene, then propene, butene, pentane. And in the same way, we would have our displayed formulas here, and we'd break them down by carbon blocks. We'll talk a little bit more about that in a second. But the main big thing to remember is with our alkenes, this C double bond C is our functional group. It makes our alkenes reactive, much more reactive than our alkanes, which is that's the useful property of alkenes. We can actually do quick, simple reactions with them. So because of that double bond, using up some of the carbon's electrons, our general formula for our alkenes is CnH2n. So you just double the number of hydrogens. Alkenes are very easy to spot from their molecular formula. So their number of hydrogens is always double their number of carbons. So they're quite easy to spot. This reminds me that we need to make sure we've got saturated and unsaturated for hydrocarbons in our head. Saturated and unsaturated has a completely different meaning when we're talking about solutions and dissolving things. But in terms of organic chemistry of our hydrocarbons, an alkane is saturated. You can't put any more atoms on it. You would have to do a substitution, like we talked about in the reactions with bromine 1. You'd have to break a bond off to put something on, because there are no double bonds in it. Alkenes are unsaturated. They're not full up. They have that double bond that we can break and then attach things to it. We can add to our molecule. We can do an addition reaction. Which is why with our reactions, our bromine water decolorizes with our alkene because we are doing an addition to the unsaturated molecule. Whereas with our alkane, we get no immediate change because you need a really long time to get the hydrogen to come off of that saturated molecule to do a substitution reaction. So let's have a little look at the mods and what some alkenes look like and how we would do the structural formula.
We have our first 3 alkenes here. Here is our ethene, 2 carbons, and our double bond. And you can see we've got our 4 bonds. Our carbon has 4 bonds as it has to have. Each hydrogen has 1 bond as it has to have. But our double bond, as you can see, can easily be broken, and we can attach other molecules to it. We've got space in this molecule, unlike our ethane, where there was no bond that was easily broken. You'd have to pull something off completely before you could replace it. So our ethene is nice and simple. Then we have our propene. Now the first thing to note, and a common mistake that people make, is not all of the bonds between the carbons are double bonds in alkenes. There's only 1 double bond in the molecule. All of the rest of the carbons are attached normally with single bonds. So this is our propene with our double bond. and our single bond to the third carbon there. And then we also have our butene. So this is our 4-carbon compound. Again, only one double bond in there. The rest are all connected by single bonds. And you may notice we can actually have an isomer of this. There is a different place we can put this double bond that will not make it just the mirror image. Obviously, if we put it at the other end, it would just be the mirror image. But if we put it in the middle, we would get a very different molecule. So this we would call but1ene, because the double bond is on carbon number 1. This we would call but2ene, because our double bond is in the middle, it's on our second carbon. And these two, you can't make them identical. It doesn't work. If you line up the double bond, there's always going to be a difference. Okay, they're definitely not identical. So they are isomers of one another. Same number of carbons, same number of hydrogens, but completely different shape. And this gets a bit more obvious with the structural formula. So if we turn these into our structural formulas, ethene would be pretty easy. My carbon block is a CH2, so I would write CH2, and then I've got another CH2. So my structural formula for ethene would be CH2CH2. And obviously my displayed formula would have that double bond in. And you'll notice that I draw them diagonally. You don't have to, you could draw them at 90 degrees, it's just because in reality they are diagonal like that, so that. So our propene, then, our first block is a CH2. Our next block is just a C and a H. And our final block is a CH3. Now, you don't have to show where the double bond is in your structural formula, guys. You can work it out by the number of hydrogens attached, because obviously this carbon only has 2 hydrogens, this carbon only has 1, which means they've obviously got a spare bond between them. So it would end up looking like this in our displayed formula. However, sometimes people like to put the double bond in, so you could, if it helps remind you where the double bond is, write this, so that you can remember that the double bond is in between. You may see that sometimes, but it doesn't have to be there. The double bond is implied by the lack of hydrogens. There's not 3 hydrogens on the end, so we know there must be a double bond. So how do we know that these two are isomers? Okay, our butenes. Well, we've said before, if they're isomers of one another, their structural formulas are going to be different. So let's do our but1ene first. So our structural formula would be CH2, CH, CH2, CH3. Yeah. Whereas our so that's our but1ene. Whereas our but2ene, if we separate it out, we would have a CH3, a CH, because there's our CH block, another CH, and then another CH3, which will give us our but2ene. So their structural formulas are not identical, definitely not. You can still tell where the double bond is, because obviously these hydrogens, there's not 2 of them, so there must be a double bond there, and this is missing one at the end. So you would get your 2 possible isomers.